start that.
Okay, so very warm welcome everyone to this seminar. Today we have Aaron Wells from Paderborn University. It's a pleasure to host him. He's going to talk about the arguments for the continuity of matter in Kant and the Châtelet. So Aaron, thank you very much for being here, and I leave it to you.
Great. Thank you. Can everyone see my screen? All right. Well,
Yes,
good. I'm very glad to be here. So I guess we can just jump right into the topic, which is a simple argument for the continuity of matter, which I've laid out in a very abbreviated form here. So the first premise is that space is continuous. The second premise is the conditional, that if space is continuous, then matter is continuous. And so the conclusion is that matter is continuous. And I'll be discussing how Emily du Châtelet and Kant both accept a form of this simple argument and how they both connect it to some kind of idealism about matter. At the same time, they differ regarding their precise conceptions of continuity, about how these premises are justified. And on a more cosmological note, they disagree about how the conclusion relates to the idea that the universe might be a material plenum. So what I want to do, the structure of the talk will be to just go through this simple argument premise by premise and reveal some ways in which maybe the argument is not as simple as it seems. But first, one historical aside as to why I'm considering these two people when you could consider other people, is that Kant is very famous, and he read du Châtelet and actually wrote about her quite a bit in his first publication on living forces. He had access to it in German, as far as we know. And so I'm not going to be making a historical argument that she influenced him in this talk, but it does, I think, kind of ratchet up the interest in comparing them, because he read her, may have been influenced by her. It's plausible that he was influenced by her. So I think it's particularly interesting, since this hasn't really been explored, her possible influence on him, to at least begin by comparing what they say, and then perhaps in subsequent work I might move towards an argument that there actually was influence. So that's just a brief explanation of why I consider these two particular figures. They're not just similar, but there are historical connections possibly as well. So turning now to the first premise, which to keep the argument simple, I put this in a very brief form, just saying that space is continuous. But the result of that is that it needs to be clarified a bit more, because historically and also today, continuity is something of a cluster concept. There are various overlapping definitions of continuity. So to say that space is continuous, that claim needs to be clarified in at least two ways. We want to know what the continuous part means, and also exactly what the space in question refers to. There's actually a fairly convenient starting point where both Kant and du Châtelet kind of have an overlapping view, and then we'll see their differences down the line. But where they agree is with respect to what I'm going to call the divisibility definition of continuity. So they accept one definition of continuity, which is that space is continuous if any of its parts is divisible into further parts. And I just want to note here that both Kant and du Châtelet are also potentialists about these parts. That means that they don't want to commit to an actual infinity of further parts that would be prior to the whole they compose. Instead, they want to say that you can divide a space or some other continuous magnitude ad infinitum. You can always keep going, and there are no limits, but you never reach an actual infinity. So that's sort of the most simple definition of continuity that appears in them, and that they both use. And then as far as the first premise goes, they want to maintain, this is just the starting point, but the most basic claim they maintain is that this property, this divisibility definition of continuity, is satisfied by the space in geometry. So whatever classical Euclidean geometry is talking about is continuous in the sense given by this divisibility definition. So then you might wonder why they think that, but first let me give you just some quotes establishing that they do think this. So Châtelet has a very pithy way of stating this. She just says, all geometrical extension is divisible to infinity. And in the context, she mentions John Kyle, who was writing in the UK and earlier in I think originally you can see in the corner, he gave these lectures in 1700, but this fourth edition was in the 1730s, I think. So an example of Kant expressing this view, it's a bit longer. So he writes, Mr. Eberhard will surely find intelligible the demonstration given by Kyle from the mere division of a straight line by infinitely many others, and would see from this that there can be no simple elements of such a line by the mere principle of geometry, that not more than one straight line can pass through two given points. This mode of proof can also yield a demonstration of the impossibility of supposing simple parts of time. So that's a bit of a tough passage, and I want to actually focus on a slightly different argument in their common source, Kyle, that is maybe a bit quicker to lay out, easier to understand. So Kyle, in this book, The Introduction to Natural Philosophy, 4th edition, 1733, gives a whole series of arguments for this conclusion that geometrical space is continuous. They, by the way, are not actually original with him. This argument that's on the screen now probably has roots in Euclid, but it's definitely developed in the Middle Ages and repeated many times by Roger Bacon, for example. But du Châtelet and Kant are reading it in Kyle, it seems like, because he's the person they both cite. So let me go through this argument really quickly, through this sort of argument sketch. So the first premise is that we assume for a reductio that geometrical space, in fact, does have some kind of indivisible elements that compose it. But premise two, if that were true, then both a unit square, so a square where all the sides have length 1, and the diagonal of this unit square could be somehow built up out of a finite number of equally sized spatial parts. But in that case, then the lengths of the sides of the square and the lengths of the diagonal would be commensurate. They'd have a common divisor because they're both built up out of equally sized parts. But we know from the Pythagorean theorem that the side and diagonal of a unit square are incommensurable. The sides have length 1, and the diagonal, of course, is length root 2. So conclusion, we have to deny the assumption, and we conclude that geometrical space does not have indivisible elements. So that's just an example of the kind of argument that they're assuming has conclusively shown that geometrical space is continuous. And this was indeed like a pretty common view at the time. It wasn't unusual to think this. Hume was one of the rare people who disagreed and thought that space is discrete, but he's very unusual. So that's sort of the simple part of this, but then there are some complications which are more or less well known, I guess. So the first complication, which I think is fairly well known, is that Euclidean geometry, any real argument that starts with classical Euclidean geometry, as Euclid actually did it, can only establish any result for certain parts of space. This is because Euclidean geometry, which uses a straight edge and compass to construct points in space, also has built-in construction limitations. It cannot construct the whole three-dimensional continuum. There will always be many, many points left out, in fact, an infinity of such points. And the whole, the depth of that worry and sort of a rigorous definition of the real plane was not available in early modernity. But as recent scholars like Vincenzo de Risi have established, I think, there were sort of worries already, even in antiquity maybe, about some of the assumptions Euclid is making, especially his assumptions that there do exist points of intersection between figures, for example, which is an assumption made by many of Euclid's proofs and which Euclid never, in fact, well proves. Usually people have to rely on some kind of intuition to fill the gap. So I just want to flag that because it's something that du Châtelet and Kant could have picked up on and been worried about, but they don't really pick up on this worry. They just kind of assume that arguments from Euclidean geometry are sufficient to show continuity in a complete way. So that's the first complication. A second complication is more a matter of comparing the two of them. I say here that Kant goes all in on the divisibility definition of continuity. What I mean by that is that he takes continuity to be sufficiently defined by this divisibility definition, and not just for space. In fact, he says that continuity in this divisibility sense just sort of is the quality of any magnitude that's continuous in general, and we can know this a priori. So he is happy to just stop with divisibility and not look for other possible definitions of continuity. So for him, he tries to make it not really a cluster concept, just use only this one simple definition of continuity. Now, Châtelet makes things more complicated for us because in addition to this definition in terms of divisibility, she has other definitions too that seem at least irreducible to the divisibility definition, and at least one of them seems to be prior to it in the sense that she uses that other definition to argue for the divisibility definition, but not the other way around. We'll see now in more detail what I mean by that. So the first of du Châtelet's other definitions may also be familiar, for those of you familiar with the history of philosophy and math. This is what I'll call the connectedness definition of continuity. It is a bit more complicated because it has two conditions. The first condition for continuity in this sense is that two parts must touch each other, in other words, be contiguous. And the second condition, using du Châtelet's words, is that these two parts must be linked together in virtue of some internal reason that prevents them from being separated. So I have a few remarks about this definition. Much more could be said. One remark is that continuity here is defined as a two-place relation between parts. So it's always about two parts that are adjacent to each other. So it's not a one-place property that you would attribute to a line or a plane or something like that, or a three-dimensional space. So second, well, before I move to the second point, let me just acknowledge or note that something like this definition famously appears in Aristotle. It's in his Physics, book 5. So Aristotle also has the divisibility definition. So he's an early example of someone with multiple definitions of continuity. So the next issue I'm going to mention for du Châtelet is something that has also been raised as a problem for Aristotle. The problem is as follows. The definition given here in terms of connectedness seems quite intuitive for material things or bodies. And du Châtelet gives an extended discussion of an example she likes, which is you have two metal hemispheres, so half spheres, and you first imagine kind of smashing them together so they're in contact. They're just touching though. So whenever you want, you can pull them apart. She says that would be sufficient for them to be contiguous, but if they're just touching, they aren't yet continuous. Instead, you need to go down to the blacksmith or whatever, to the metal shop, and melt them or fuse them together, and then they become continuous. But of course, as she notes, you can still separate them again, with enough force. So it's not like the linking together that comes about here is some magical metaphysical glue. It's still just sort of something physical. So far, so good for bodies and stuff, but she wants this definition to apply not just to bodies and matter, physical things, but to parts of space and also to geometrical figures. And here it becomes unclear how this is supposed to work. It's relatively straightforward what it means for two geometrical figures to be contiguous if they touch each other. But then what is the extra linking together in virtue of internal reason? What is that for two adjacent parts of space or two geometrical figures that are touching? It's not so clear how that works. Some people have given some rather involved accounts of how this might work in Aristotle, like Christian Pfeiffer, I think. Anyway, it's a bit of a mystery to me, and du Châtelet at least does not explain exactly how that would go. So that's a complication there. And yet there's at least one more definition of continuity that comes up in du Châtelet, and maybe I should have put this in a bigger font because I take this one to have a kind of priority over the others. it has a priority of place in the book that I'm quoting from, the Institution, because it comes first. It actually, this definition appears before du Châtelet really gets into talking about space or time at all. And then I'll also suggest that it has an argumentative priority because she uses this last definition to argue for the divisibility ad infinitum of space, time, and matter. So this final definition, I'll call the continuous function definition of continuity. And the way I'm glossing this, the idea is that a function's graph must have a tangent at every point. So that technically is applying to a function, but her idea is to use this property of functions and graphs as a criterion for the continuity of processes. So there's a bit of a complexity here where you have a mathematical representation, and maybe that in some sense is what's in the first instance continuous, but she thinks that tells us about the continuity of the underlying change of process described by the function. And in particular, she thinks we can determine whether a graph satisfies this continuous function definition by checking if the graph is smooth in the sense of lacking sharp angular bends. And interestingly, she's not, doesn't have modern analysis, but she does recognize that the angular graph is continuous in many intuitive senses. She seems to recognize that it would satisfy her other two definitions of continuity. After all, the fact that it has angular bends does not mean it has any gaps. It just, well, the difference is, it seems like that the angular graph, even though it might count as continuous in the modern sense, is not what we would call everywhere differentiable, because you can't always draw a well-defined tangent line at every point. So again, I wouldn't say that she's fully grasped these distinctions because no one had at this time, but she's sensing with this definition that she's sensing that this definition in terms of the continuous function is stronger than the other two definitions because she considers cases where those other two definitions are satisfied, but because of the angular bends, this definition is not satisfied. There's more discussion of this, by the way, with respect to du Châtelet in Mark Wilson's recent book, Imitation of Rigor, in the top right. So the last point I want to make on this definition is about what I call its argumentative priority. So she does try to use this definition to argue that space, time, and matter are divisible. Roughly, the way this argument goes is she thinks that once you grant that there are processes that satisfy this continuous function definition, then you imagine these processes actually kind of running out through space and time, and whatever is undergoing the process, for example, a body that's moving, has to go through every conceivable point in space and time in its path. So that means, since we can conceive points ad infinitum, she thinks there have to be enough points for these processes to go through, so space has to satisfy the divisibility definition. I don't know if that argument is that conclusive, but she tries to argue this way, which gives us insight into how she conceives of the priority of these definitions. She uses this one to argue for the other definitions and not vice versa. So this may be, for her, the most fundamental definition. And I won't get into the details here, but I just want to reiterate that this doesn't seem to appear in Kant, and neither really does the previous definition of continuity in terms of contiguity, in part because I think Kant would say that for two parts that are next to each other to be held together, you can't just talk about continuity anymore. You have to bring in causal categories, and that's sort of a whole other discussion. So he wouldn't want to subsume the issues that du Châtelet is talking about with her two fused hemispheres, for example, under the rubric of continuity. He'd want to talk about it somewhere else when he talks about causality. Okay, so enough of the first premise. Let's move to the conditional, crucial middle premise, that if space is continuous in one of the ways that we've been discussing, then matter is also continuous. So first, I just want to give you a sense of what this conditional means for these two philosophers and why they might endorse it. So du Châtelet is fairly upfront with a principle that seems to lead to a kind of conditional like this, because she tells us early in her book, The Institution, that the same thing happens in nature as in geometry. We'll see that there are some qualifications for this later on, but at least many things happen in nature as they do in geometry, as we'll find out. One reason why she holds this principle is that she thinks that material nature and geometry are both partly dependent on our minds. So she thinks that matter is partly mind dependent, and then geometrical objects are even more mind dependent. So it's maybe not surprising they have some similar structure. It's not as if matter is fully out there, outside of our heads, as it were, and geometry is just inside, to use a very crude metaphor. Instead, they're both already have some mind dependence mingled in. So there's less of a problem in seeing why they would have the same structure. So more explicitly, she does have a kind of argument against there being indivisible parts of matter, which is also on this slide. Her argument's very condensed, but basically she says we can assume in premise one for reductio that matter does have such indivisible parts, but, and this is important, if these parts are supposed to compose matter, like actually add up to extended substances with a finite volume, if so, these parts have to take up space. So each part has to have a finite volume. It can't just be infinitesimally small. So that's a very big assumption, but I will say it's a very common assumption at the time that they assume that you can't take an infinity of points, for example, and put them together into a finitely sized space. So given that assumption, the third premise is that if there are these parts themselves have parts, and that means that they aren't indivisible, and that contradicts our initial assumption for reductio, and we're supposed to conclude that matter does not have indivisible parts after all. There's more, she says more about this topic too, but I'm going to move on to a passage that I think illustrates why for her this issue is not sort of a merely abstruse metaphysical question. She does kind of suggest there's a distinction, and I'll get to this later, between the metaphysical divisibility of matter and its physical divisibility. But the conclusion of the argument I just stated is supposed to have for her quite important consequences for explanation in physics. So to give you a sense of why, I'll just read this passage. She writes, I call mechanical principles the size, figure, motion, and situation of parts, and I call physical principles all those qualities of which we have not yet found the mechanical ground, or raison in her words, such as elasticity, electricity, etc., also gravity, by the way. But there must be an infinity of corpuscles that our senses cannot follow in their decomposition. Therefore, there is an infinity of physical qualities of which we will never know the mechanical grounds. There must be an infinite number of these grounds by which by their nature must escape us. So in brief, what she's saying here is that matter has an indefinite number of parts. Our senses and our abilities are sort of finite. We can always keep building better microscopes, for example, or refining our senses, but only in finite degrees. And so we'll be able to gradually observe lower and lower levels of composition in reality, smaller and smaller parts, and thus further and further levels of what she calls mechanical principles, where there are material parts that have a certain size, figure, and motion. But this process is infinite for us, or at least indefinite. We'll always keep going to further and further lower levels. We'll never reach a mereologically lowest level of material reality. So what this means is that our mechanical principles and mechanical explanations will never be complete. We can never explain everything in terms of mechanical principles. We always have to rely on these physical principles where we haven't yet found their mechanical grounds. That's not to say that she doesn't think that, say, elasticity could never be mechanically explained. It's just there's no guarantee that we will. Depends on what level that explanation is at, and maybe we'll just, in fact, never get there if it's very far down. So this is supposed to illustrate how her doctrine of the divisibility of matter actually has some concrete implications for how we conceive of our explanations in science. So it's not just an abstruse metaphysical question once again. So let's turn to Kant. As usual, his quotes are a bit more difficult to understand maybe, but he has some very clear statements throughout his career that seem to entail the kind of conditional that I am calling premise 2 in the argument. So early on in his 1770 Latin dissertation, the inaugural dissertation, he writes, "Nature is completely subject to the prescriptions of geometry in respect of all the properties of space which are demonstrated in geometry." That's a very strong claim. So then 20 years later, after he's written all 3 critiques, he comes back to this topic and makes a pretty similar points. And we'll see that there are kind of 2 arguments here, though. To read out the quote, he says, "One cannot here prevaricate by claiming that concrete time and space are not subject to that which mathematics demonstrates of its abstract space and time as a being of the imagination. For not only in this way would physics, in very many cases, for example, in the laws of falling bodies, have to be concerned about lapsing into error if it follows exactly the apodictic doctrines of geometry, but it can also be just as apodictically demonstrated that each thing in space, each alteration in time, as soon as it occupies a portion of space or time, can be divided into just as many things or alterations as are the space or time which it occupies." I want to take this last quote maybe in reverse order. So the Arabic number 2 here that I've inserted seems very similar to that argument from du Châtelet that I just was discussing earlier. Maybe they have different reasons for the premises, but the basic thought here is that you have a thing that's in space, matter is occupying space, and then, well, that space has a certain compositional structure, it can be divided indefinitely, and, well, matter is occupying it, therefore matter also has that compositional structure. I think the roots of Kant's endorsing this view are different than du Châtelet's, and I won't get into all of them, it relates to his own version of idealism. But I think it's notable that he's laying out a very similar argument to her. But then Arabic number 1 is more of the argument that if you couldn't draw the kind of conditional claims that are in this premise, then there'd be some kind of problem in doing mathematical physics. Your mathematical propositions would not be exactly correct of physics, and then your physical laws, which are in mathematical language, would just be wrong. Some people would just accept this consequence, but not Kant here. He wants there to be an exact correspondence between math and physics. We'll see in a few more slides, du Châtelet does not agree. So this is a big difference between them. So one more thing about the first sentence, who is prevaricating? So Kant is here addressing Eberhard, who is a follower of Christian Wolff. And Christian Wolff was a big influence on du Châtelet in some ways, but this is a case where they disagree. Kant and du Châtelet are on the same side of this debate in endorsing these kinds of conditionals, like if space is continuous, then matter is continuous, whereas Wolff and his followers tend to distinguish between concrete space and time as having one structure and abstract space and time as just being a mere being of the imagination. That's also something, by the way, that Voltaire did. Voltaire and du Châtelet were very close to each other. And so it's also interesting that du Châtelet dramatically disagrees with Voltaire on that point as well. So that's just some historical context. So now let me note a few points of similarity between why they might endorse this conditional that I've hinted at before. Both Kant and du Châtelet hold that matter is non-fundamental, that it's a phenomenon. They both use that term. And again, this makes it easier for them to argue that matter and geometrical space have the same compositional structure. But also it allows them to limit the conclusion of the simple argument, limit its scope. So they don't want to conclude that every single created thing is continuous. So Kant, this might be very familiar, sort of the textbook Kant says that space is not a property of a thing in itself, says the same thing about time. This means that the question of divisibility into spatial parts, and hence this question of continuity, does not really apply to things in themselves. So there's some sense in which created things can't be said to be continuous, namely as things in themselves, or things in themselves aren't continuous. However you read this, Likewise, du Châtelet goes even further. She explicitly commits to substances that are simple and non-extended at some more fundamental level of created reality. So again, by endorsing this kind of either idealism or view that matter is a phenomenon, whatever you want to call it, it makes this premise easier to justify, but it also limits the conclusion because matter doesn't turn out to be all there is in the created world. There's a bunch of other substances too, which are maybe even more fundamental. So now some more complicated things about this conditional. So first of all, du Châtelet, in fact, despite her slogan that things are in nature as they are in geometry, that's only approximately true, it turns out. So she says actually that our mathematical representations are always imprecise in sort of an inevitable way and only approximately true of the material world. I want to stress, this is not completely clear from this slide, but she thinks that this approximation is inevitably what she calls considerable. So you can never, no matter how far you go in refining your mathematical representations, it will still be significant. So this is a difference from some other figures like Leibniz, who might say, yeah, there's always approximation, but we can reduce it to such a, we can reduce the error ad infinitum, so we don't have to worry about it. Du Châtelet is a bit more worried about it. And that might suggest that since continuity is not really something approximate, it's an all or nothing property of matter, that she shouldn't be quite so confident about inferring from mathematical properties like the continuity of Euclidean space to properties of matter. That's a complication for her. Kant, there's also a complication which you might see as a kind of bad company worry about this conditional premise. The idea is that there are other conditional claims that move from geometry to matter that Kant does not accept. And there's sort of you might wonder why, if he does accept one for the continuity of matter, he doesn't accept the other. What's the justification for that? So in particular, he grants that geometry presupposes a space with no outer limits and no internal gaps, kind of topologically, as it were. But he doesn't think you can conclude from that matter, that the matter that fills space, is an unbounded plenum that would have what he calls no empty spaces. We'll see on the next slide, I think, that showing that would require empirical evidence, which will never be available to us. And that's all well and good, but you might think he's blocked that inference because it's an empirical question. Why can he run this premise to this conditional on a purely a priori basis? Shouldn't the continuity of matter turn out to be empirical as well? Now, there has been some suggestion in the literature that either Kant did make the continuity of matter empirical, that's something Michael Friedman has suggested, or that he should have. That's something Maria Stan has suggested, but there's not too much evidence that he actually did. And we can talk more about this in Q&A. And in any case, it doesn't really address this worry of this apparent inconsistency in most of his discussions between how he treats continuity and how he treats this filling space issue. So, but more detail on that is needed. So here's an actual quote about these empty spaces. This is, by the way, as he's saying in this quote, this comes very near the end of his Metaphysical Foundations of Natural Science. Kant writes, the well-known question as to the admissibility of empty spaces in the world may serve as our conclusion. The possibility of such spaces cannot be disputed, for space is required for all forces of matter, and since it also contains the conditions of the laws of diffusion of these forces, space, is necessarily presupposed prior to all matter. Thus, attractive force is attributed to matter insofar as it occupies the space around itself through attraction, without at the same time filling the space. Thus, the space can be thought as empty. End of quote. A lot going on there, but very briefly, what he's saying is empty spaces aren't ruled out metaphysically. So note that it's not just a logical possibility, it's some kind of the metaphysics of nature or the metaphysics of matter. Whatever that is, doesn't rule out empty spaces. That's why he's talking about forces here, and not just that we can conceive of empty space. He's saying that his metaphysical account of force doesn't rule it out. So they're not ruled out metaphysically, and therefore, if the question of empty spaces were to be settled somehow, then we would need empirical evidence for or against empty spaces, but that consequent Kant goes on to deny. Why? It's rather cryptic, but he says that all experience yields only comparatively empty spaces for our cognition. I'm not going to try to unpack that, but just structurally, the way this argument works is he's running a modus tollens. Because that conclusion doesn't obtain, we can't actually be sure if empty spaces exist. Just a quick point of contrast, du Châtelet does not get into all of this because she very quickly just says, empty spaces are ruled out a priori by the principle of sufficient reason. There's no need to go empirical here at all. We'll see at the very end of the talk that this is a case where Kant thinks it's empirical and Châtelet doesn't, but there's another issue where it's the reverse. So they interestingly just sort of diverge in terms of what they consider more metaphysical and what they take to be an empirical question. Okay, so now much could be said about this conclusion that matter is continuous. I just want to mention sort of 2 points. One is this puzzle that I think is a bit neglected, or rather the specific version of this puzzle is neglected, I would say. So they're concluding that matter is continuous. And what this means for them, remember, is not that matter has an actual infinity of parts, but that it's infinitely divisible into potential parts. So this introduces potentiality into matter in some important way. And they go on to suggest, both of them, that these potential parts of matter actually depend on wholes. And they also seem to depend on acts of division. So very simple example, you have a cake that is not yet divided into parts. The cake does not yet determine how many slices you slice it into. That's up to the slicer, as it were. You can cut into 4 parts if people are very hungry, or into 10, or whatever. Of course, though, that's, we would think, sort of a limited case, because at some level of composition, we might imagine the parts do precede the whole. There are some subatomic entities that do compose the cake. Well, that's not what du Châtelet and Kant seem to think. They seem to think that potentiality, that sliceability of the cake is how it is all the way down indefinitely. There's no lowest level. So that's a slightly mind-boggling view. And in fact, they don't seem to consistently adhere to it all the time. There are some cases of this that have been discussed in the literature, but I'm going to focus on a case where it's less discussed, which is that both du Châtelet and Kant seem to be realists about infinitesimal forces or other infinitesimal properties. And they treat those infinitesimal forces as having physical reality and as summing, in big scare quotes, to finite forces. So you take an infinite number of infinitesimals, they somehow sum up to a finite quantity. There are some worries, of course, about exactly how that math would work, but I just want to focus on the metaphysics here. They're not treating these infinitesimals as merely potential and depending on wholes. Instead, those infinitesimal forces seem to be prior to the finite measurable forces that they sum up to. So textual evidence to follow. I don't know why that happened, but so from du Châtelet, in her final chapter of the Institution, which is on live forces, force vive, vis viva, however you want to call it, she writes things like this, quote, an infinitely small live force can only become a finite live force when it is repeated an infinite number of times and accumulated by an infinity of successive pressures, pression, in the body that receives the motion. This infinitely small force is the elements of the live force. So that's compositional language here. So it seems like, at face value, prima facie, this is not just a mathematical idealization. These moments of live force are somehow physically real. They really are pressures or effects of dead force. So they seem to be really out there, and they sum to something that we can measure finitely. So they seem to precede the wholes that they compose. Likewise in Kant, though, again, it's especially difficult to understand what Kant's saying. Maybe it's easier to read first this quote from his 1760s negative magnitudes essay, which doesn't use as much technical Kant vocabulary. In that essay, he writes, if there are forces which operate continuously for a given time so as to produce movements, and gravity to all appearances is such a force, then the force which gravity exercises at the very beginning or in a state of rest must be infinitely small in comparison with that which it communicates over a period of time. And then in the first critique, the second quote, he writes, and this is a difficult one, if one regards the reality if one regards this reality as cause, whether of the sensation or of another reality in appearance, for example, an alteration, then one calls the degree of reality as cause a moment, for example, the moment of gravity, because indeed the degree designates only that magnitude, the apprehension of which is not successive, but instantaneous. So that is hard to understand, including the idea of instantaneous apprehension, but I'm going to sort of punt to Daniel Sutherland, who is an actual expert on this topic, and he agrees with my reading that there are many passages like this one that seem to be endorsing a kind of infinitesimal realism in Kant. What he wants to do, though, is to say, well, there are other passages that are Kant's more considered view that are potentialist and would handle infinitesimals in terms of limits, and so we should read Kant that way. And that may well be the most charitable option, but there's still a sort of textual tension in Kant that suggests that Kant himself didn't quite have this figured out. So I think this is a point of similarity between them, for better or worse, between Châtelet and Kant, that they both seem to have trouble consistently saying that the parts of matter are determined by or grounded in wholes. They sometimes want to say that certain kinds of infinitely small entities actually are prior to whatever they compose. So one last point here, I flagged this earlier, about, which of them think that a given question is metaphysical and which of them thinks it's empirical. So this conclusion of the simple argument establishes this sort of in principle or metaphysical divisibility of matter. It's hard to say exactly what that means, but again, think of these arguments where they're saying a piece of matter occupies space, and therefore it has the same structure as space, so it has parts, it's extended in space. That doesn't tell you automatically anything about what sort of physical mechanism could actually divide it, or even if there is such a mechanism. It might just be that in the world we live in, there are these kinds of metaphysically divisible lumps of stuff out there, but there's nothing, maybe besides God, that could actually separate them. So Châtelet uses the terminology of real separation. Can you take, for every part of matter, absolutely everyone, as far as we can divide it ad infinitum, for any given part of matter, can you really separate it by some physical mechanism, so move it away from its adjacent parts? How can we show that to be true? Kant actually thinks we can show it to be true, that we can use metaphysics to show that actually every part of matter has repulsive force, and therefore it can really be separated from its adjacent parts. I won't get into that argument here, but he definitely thinks yes, and it's a matter of metaphysics. Châtelet is maybe a bit hesitant, but it seems to her like an open empirical question. She suggests sometimes that it's probably likely that there's some level where, nature just stops making things really separable, and there are these kind of natural minima. But then she also thinks that there's incorporeal ether, sort of imponderable matter that is swimming around matter, not weighing anything, and can maybe dissolve even these natural minima. So it seems to me like for her, it's just an open empirical question. So that's one last kind of difference between them. They both start by making a distinction between metaphysical and physical divisibility, but then how they answer it is different. And with that, I will conclude. Here, though, are some few citations that were helpful to me, or I guess a citation of myself. But anyway, I look forward to discussing this with you, and thank you.
Thank you. Thanks a lot for this beautiful talk. So we now start with the Q&A. Are there some questions? Yes, Laura.
Yeah, thank you for the talk. Very interesting. And I would like to start to something that was particularly interesting to me. So the connection between so what you said about the connection between the phenomenon and the notion of divisibility. Mm-hmm. So the idea that both, if I correctly understood, both Kant and what is divisible is essentially what we call the phenomenon. Is it right? So both have this position. And what is interesting to me is the fact that we are talking about divisibility and phenomenon. So that means divisibility and all the things that are connected with sensible knowledge and with our knowledge. So in the sense that the notion of divisibility is necessarily connected with everything that we know by perception, so by experience. Okay, and what you said also is that this definition of divisibility is somehow connected with, cannot be separated by a knowledge that imply the influence of human mind. So in this sense, you have the connection between what we know and what is divisible. This argument is reminds me, recalls me to Leibniz's position. That means that according to him, we have two different definitions of, let's say, what is divisible in the physical world. So you can divide matter to infinite. So you can you don't have the particles. So you don't have the indivisible particles. So from the one side, so this is the empirical world, the physical world, and on the other side you have the metaphysical world, so the spiritual atomism, let's say, the monads. But that, and this is one point. So I think we are dealing with a debate that originates from Leibniz, and also you mentioned Wolff. So through Wolff directly to Leibniz, but also indirectly through Wolff. But the interesting part of your talk is also the final, the conclusion. So the what you said about the distinction between potential and actual. So here I found maybe some difficulties or some problems. I don't know, because of the link between what is actual, so the reality, the physical reality on the one side, and what is potential, so the metaphysical part. Is it right, this parallelism, or am I misunderstanding something in this final distinction? So you connect actual and physical world and potential with metaphysical world in the sense? No, I would think it would be the opposite. Yeah. Okay. Right? Okay. So I found here a problem in relation to what I said at the beginning. I don't know if the question is clear, but if you can say something more about this, thank you. Yeah, good. Well, okay. If it's clear, the question. If it's not clear, I can try to. Well, there's a couple things. Yeah, I'll try to do my best. Okay. So maybe we can start by going back to Leibniz. Yeah, it's totally right that this is in the legacy of Leibniz. You can see the bottom here. A lot of this is coming from a paper I wrote for this edition of this book between Leibniz student and Kant. So it's all about post-latency and context. So the young Kant. Yeah. So as you know, I'm sure, like in Leibniz, it often comes up that something real, a genuinely real thing has to be simple. That's like a Leibnizian principle. So yeah, I think that is a principle that both du Châtelet and Kant are pretty sympathetic to, coming out of Leibniz. So then, yeah, you could extrapolate from that some idea that in some classical sense of actuality, it's only these simple things that sort of have full actuality. Like, I don't know if they all want to talk this way, but that this might address your last question about. So if you take the level of Leibnizian monads, Kantian things in themselves, or
Châteletian substances to be the most fundamental and the most real, in some way, maybe it's also, that's where the creative world is fully actual, because it's just there in a way that's not dependent on further acts of finite beings. Whereas matter, remember the slicing the cake example, you have some matter out there that's just somehow indeterminate, probably because it's partly mind dependent, and it has to be determined, or it can be determined by acts of finite minds into further and further parts. So you might think, yeah, that there are these, a monad in some sense just kind of is as it is, and then and the same goes maybe for a thing in itself, or du Châteletian simple. So it has a kind of actuality once God creates it that that matter does not. So the physical world would then be less less actual in that classical Aristotelian sense than the metaphysical world, in the sense that Leibniz talks about actuality. It's all actual, God actualizes everything, but there, as you know, there are different senses of actuality. There's the kind of classic ancient sense from Aristotle, and then there's this sense from Leibniz that's more, what analytic metaphysicians talk about these days, like the actual world. So one other point I want to make, though, that I didn't get into this history, but you may know that in the 1740s, there was a big controversy about monads in Germany, known as the monad controversy, the Monadenstreit. And what's interesting about the Monadenstreit is that they really focus, the streit is about the divisibility of matter, and really only about that issue, divisibility versus indivisibility. Whereas if you go back to Leibniz, as we were kind of, this came up in your question, for Leibniz, there are maybe other issues on the table as well. And one of the very important issues is this issue of priority, whether the parts precede the whole in some way, ground the whole, or whether the whole grounds the parts. And so that is very clearly addressed. That priority question comes up a lot in Leibniz. And then I think it's a bit pushed to the wayside in the 1740s in the Monadenstreit, where everyone's talking about divisibility. And then you're in a weird place when you get to Kant, because his antinomies, when they talk about parts and wholes in the first critique, they are talking about divisibility, but he still has to be committed in some way to some kind of, one's determining the other in some way, either the parts determine the wholes or vice versa. You can't have both. So he seems to face these questions of which way is it, and it's hard to know exactly what his answer is. That's part of what I was getting into at the end of the talk. And I think some similar issues arise for du Châtelet. One final thing just about the Monadenstreit that I want to mention as a historical fun thing is that du Châtelet was actually asked by one of the Bernoullis, maybe Johann II Bernoulli, asked to participate in the monad controversy. He wrote her a letter and said, "Can you defend monads? You'd be great at doing it." It was a few years after she wrote the book I'm talking about, and she was busy translating Newton's Principia, so she wrote back and said, "I'd love to. Monads are, the foundations of sound metaphysics, but I'm too busy." So there's this other possible world where she could have been a public participant in that Monadenstreit, which would have been very interesting, but unfortunately not. So just want to say there's a little bit of connection there too. So did that help with your question? I don't know.
Thank you. Yeah. Thank you. A lot of things. Yeah.
Okay, so Laura.
So thank you very much. It was really interesting. So two questions, they come a little bit from ancient philosophy. So if they are a bit out, excuse me in advance. So the first one is, just two curiosities about du Châtelet. So the first one is, does she admit for some kind of geometrical or immaterial matter? Maybe you were mentioning that very briefly in the end. So, I mean, something which is matter, but it's immaterial, non-corporeal, and it should serve as a matter or as a substrate within geometry, but not within physics.
Okay.
And and the second one, and if yes, how does she distinguish something like that from space? That would be the first curiosity. And the second one is, so from the terminological point of view, when she speaks of geometrical bodies and physical bodies, does she always use the word body? So in many languages you have this problem, both in ancient and modern languages, but there are so different strategies to distinguish them. So what makes the difference? Is it matter which makes a difference in order to discriminate a physical body from a geometrical one? Or is it some kind of fullness? So in late antiquity, sometimes some kind of fullness is mentioned in order to distinguish the physical bodies, all the bodies that you find so in this world, from the geometrical one, which are extended. They are somehow two-dimensional solids, but are not properly bodies in the fullest sense of the term. Yeah, thank you.
Oh, good. Okay, thanks. Those are great questions. So first, she thinks that space and time are dependent on matter in some way. Like, she's a relationalist about space and time. So she thinks that material stuff does actually precede space and time, and also, as a result, geometrical extension. So what you were alluding to in the talk, what I was talking about is not actually a kind of matter that could undergird geometry. It's matter that doesn't have mass. So it's still matter. It's still physical in a broader sense. Like an ancient philosopher would, I'm sure, consider it physical because it exerts force. For example, it's a cause. It satisfies the Eleatic principle. So an example of this for her would be like fire. These kind of imponderable fluids that are rushing around everywhere and acting somehow on ponderable matter, on regular matter. Now, for her, this is all kind of hypothetical, but she is very interested in the hypothesis. But that's not going to serve an epistemic role in geometry for her. Instead, she has more of an abstractionist account where you take, I don't know how it works, but somehow you take relations between the real actual bodies and you abstract from them and you somehow get an abstract space, and then that's where geometry operates. But as I mentioned, there's an inevitable loss of precision, as she puts it. So somehow there's not going to be an exact mapping between the geometrical stuff that you abstract away and what you're abstracting from in matter. So physics is always going to be a little bit approximate for her. But that's a super interesting question. So then, yeah, this question about the terminology. So she does talk about geometrical figures, figures, that are not bodies, corps. So there are different terms for her. And yeah, I think as a first pass, it is correct to say that a figure does not have, it's not material, in part because of what I was just talking about, the fact that it's abstracted from matter. She, in fact, talks about two kinds of, well, I can't quite say that there are two kinds of objects, but she talks about abstrait, plural, versus concret, plural. So you might call that abstracta versus concreta, two kinds of thing. The geometrical objects and numbers are abstracta, and bodies are examples of concreta. So two probably would be souls in some sense, because they're not abstracted from anything. So it doesn't have to be material to be concrete. But you mentioned too, this is also in her view, this maybe more Aristotelian idea of like the fullness or something of the bodies. So I'm not sure I'm picking up on this entirely, but she does say this thing that is also in Aristotle, that really in nature, everything has three dimensions. It's all, everything is three-dimensionally extended, and then planes and lines and finally points, those could only come about through abstraction. So maybe for three-dimensional stuff, there's maybe a more fine-grained distinction between the way in which geometrical solids fill space and the way bodies fill space. But then for the objects of plane geometry, like the lines and figures and the points, those are all like they could, in some way, they're never really in, I don't know, maybe they're there, I don't know. She at least says that everything is three-dimensional and then we abstract all the lower dimensions away from that. So that sounds to me very Aristotelian, but I don't know what you think.
Yes, thank you. I think from everything you said, it sounds very Aristotelian, and also what you were saying before to Laura about the infinity, so actual and potential. Yeah, I think also the abstraction process, in considering geometry, many points, sound very Aristotelian as a background.
Yeah, one note of caution though, because I had like a few weeks ago, like Dominic Perler, like I've had Aristotelians say, oh, this just sounds like the abstraction sounds exactly like Aristotle. And I think she, as far as the process of abstraction goes, she takes pains to distance herself from at least how I understand an Aristotelian account, because she thinks that you are actively creating new abstract entities when you abstract. You're not just, at least this is how I read it, you're not just picking out properties that really are there in the real material thing and like considering them apart from the material thing, which is why there ends up being this whole problem of approximation. So in the terminology of contemporary Anglophone philosophy of science, I would say that for her, like, it's really more like idealization, where you're creating and transforming, you're bringing about these new properties in your abstract, once you've abstracted from matter, and not just sort of subtracting away some properties that are out there in the material things after all.
Yeah, you're right.
Yeah.
I think Aristotle, only in Aristotle you have this subtraction of matter, but then from Middle Ages on, I mean, when we speak about abstraction, there is this Aristotle in the background, but actually it's always a form to be taken out. So
okay, good.
Thank you.
Okay, it's interesting.
Yeah,
Sorry,
thank you.
and a question about concretely the sources. Sorry.
Oh yeah,
No.
of course.
There's another question, Silvia, for other people. Sorry.
No,
It's connected. No, it's just connected
ahead.
to this topic. It's just connected to that. So the source Aristotle is mentioned about this by du Châtelet about this problem, or you don't have any kind of reference? Okay, just that. This was just that.
Not about this. She mentions Aristotle a few times, but it's always
it's not relevant.
It's not relevant, and it's very negative usually. So
okay, thanks. Sorry, Silvia.
Okay, no, don't worry. Okay, so let's go back to Leibniz again. Well, in some sense, it's related to what the second Laura asked. So Laura Maronjo asked, in the sense that, but also with the previous, I mean, the first question. So I would like to deepen a little bit more the question about extension space in the Châtelet, because we know in Leibniz, space is not something fundamental, it's something that, so to speak, emerge on the ground of metaphysical foundation of extension and all the metaphysical apparatus of the monads. I wanted to ask you this. It's true that there are traces of Leibniz, but in any author, let's say, working in the 30s and the 18th century, there are traces of Leibniz, critical or not. I mean, of course, it's... my question is, what about the Châtelet's position with respect to the doctrine of the physical monadology? Because one thing is saying what Leibniz thought about monads and what he wrote in manuscripts that were not published, okay, apart from some works, but at that time the whole corpora of Leibniz work was not available. So it's clear that du Châtelet of course had in her mind Leibniz, but most Leibnizians and also Cartesians, let's say, that were criticizing Leibniz in some way. So my question is, first, did you make some extensive research on du Châtelet's notion of extension with respect to the doctrines of physical monads that were diffused at that time, widespread at that time in Europe? I asked this question for obvious reasons, because Kant wrote a physical monadology in the 50s. So it means, I mean, whereas for Kant, there's no doubt, let's say. I would like to know more about du Châtelet. So that's my first question. If you like, I can ask you the whole questions. Otherwise, you answer to this, and then you
can go ahead, I think.
Okay, so then there is another point that concerns the first part of your talk when you mentioned this continuous function definition that we find or you interpret it as continuous function definition that Châtelet provides. But whereas it's clear to me how and why she uses that for space, it's not entirely clear how she can manage to apply it to time. And I say that because time is one-dimensional. So it's clear that she has in mind the fact that we have always to consider space and time together. So this is the first answer that comes to my mind, but I want to know what you think about it. So because of course, if you take the slide again on your screen, maybe the other people also can read it again.
This one?
Yeah, exactly, precisely this. So to be continuous, a function's graph must have a tangent at every point, right? So this is the criterion to obtain the continuity of processes, and this is something that can be easily applied to space or easier in an easier way, let's say. But what about time? So this is so the tangent at every point. So she has a linear understanding of time. Does she has? I mean, that's the question. So it's easier to me to apply this to space rather than to time. And then the third question, it's more. You read the passage, okay, it's a translation, the one that you read from the Châtelet's work on when she talks about the infinite number of corpuscles or the infinite numbers of particles that we might find in nature, blah, blah, blah. But what's the term that she uses? Because in Kant, we have a clear definition, or better, a clear distinction, and we have it in the Antinomy and in other works, at least in the critical period. There is a clear distinction between infinity and also what is indefinite, let's say. So one thing is to have or to think of an indefinite number of particles or parts, let's say, of a whole. Another thing is to define infinity. Kant says we have to eliminate from philosophy the mathematical notion of infinity if we want to, or better, from cosmology, if we want to get rid of antinomies and paradoxes and so on. But we have to admit one cosmological principle that is compatible with critical philosophy, and that admits, synthesis, let's say, ad infinitum, synthesis of division, let's say, or synthesis of regression that concerns, in this case, the second antinomy, what is discussed in the second antinomy. So the divisibility of matter is admitted as long as the synthesis can go on. And so it relies on the fact that empirically speaking, I can continue the division procedure in my research. So my knowledge, okay, of the world, of the empirical world, can proceed as long as I can proceed in this synthetic activity. The most important thing is that I don't assume that, or I cannot say with certainty, with apodictic certainty, that matter is infinitely divisible, but just indefinitely. So did you think about this aspect of Kant? Do you think that is different of Kant's thought? Do you think that there is a difference? I think that there is a difference with Châtelet in the sense that Kant, of course, thought about it within the framework of his transcendental philosophy, but do you see analogies and so on? So that's all.
Okay, maybe I'll take the third point first. I think I have a straightforward answer to that. I think they're both potentialists about divisibility. I was trying to stress that, yeah, in the talk. Like when Châtelet is talking about that our infinite ability to further and further, look at further and further smaller parts of matter. I don't think she wants to thereby be committed to an actual infinity of those parts of matter. She's very clear about that elsewhere, I would say. She thinks that if you are committed to that, then you get into all these Zeno paradoxes immediately, which doesn't actually follow, but even her thought is that with the intervening assumption that if there are actual parts of matter, they can't have infinitely small extension. So if there's an infinity of them, then you get, she says, the universe in a grain of sand or something. So I think she definitely rejects any kind of actualism about those parts of matter. Now, yes, she does say, in that quote that I read, something about there's infinitely many, physical forces that we'll never be able to explain, and infinitely many mechanical parts. But I think she has to be read as talking about potential infinity or divisibility ad infinitum. And it was quite common in the early modern period for people to talk in terms of infinity when they don't mean actual infinity, they mean potential infinity. So I think actually she's very similar to Kant's resolution of the antinomies, the mathematical antinomies, and that they're both potentialists. And actually in the forthcoming piece I cite on the last slide, I have a very brief discussion of that where I try to say that although their motivations might be different, she doesn't actually fall into either the thesis or the antithesis that Kant discusses in his second antinomy, the one that's about material composition. I do have a side note about Kant, though, because you said something about how he rejects the concept of infinity in cosmology, and maybe I would just push back a little bit. I don't think he rejects the concept of infinity. I think he thinks the concept of infinity is a totally coherent concept. So in his metaphysics lectures, he talks about inferences you can make with the concept of infinity. The problem is applying that concept to phenomena, and especially the phenomenal world. So he thinks you can just reason about conceivable infinite noumena or whatever, things, systems that are infinite using the concept of infinity, and that's fine. The problem is once you start to apply it to the world. Maybe you agree, but I don't know.
Well, it's just, I of course was referring to what he called the regressive. So of course, for the progressive synthesis, you can do whatever you want. So there's no antinomy that is generated in that case. But when you do the regression, so, then...
Yeah, but no, well, maybe this is very heterodox of me, but I think that he thinks we have, I don't think he thinks there's a self-contradiction in the concept of an actual infinity. There's just a contradiction when you try to use that concept, apply it to the world, to anything spatial, temporal, because those they can't be actual infinites for him.
Well, it's a bit tricky in the sense I've read an article about it.
Okay.
It goes in infinitum and indefinite. Sorry.
Oh yeah,
An infinitum ad infinitum. So apparently, so he plays in the second antinomy with a notion of infinity that, of course, cannot be the actual infinity or the infinity that we used in the 20th century, or in set theory and so on. So it's not the same thing, of course, but I've shown how Zermelo, first Cantor and then Zermelo, read and commented on the antinomy, and how they found basically that it's, let's say, tricky, or at least it's more complex than expected, the notion of infinity that Kant handles in the second antinomy. So it's intriguing because it's a sort of so he distinguishes the way in which we do regressive synthesis in imagine a line, a word line, right? Okay, so I imagine the history, so to speak, of the universe back in time and space, and of course we all know how this story goes for what concerns the first antinomy. But in the second antinomy, I look at matter, so to speak, or at the whole intensively. So I want to look at its internal parts in the process of division. Okay. So he says, when in order not to encounter contradictions, what you have to do is to assume that you can progress in the synthesis in indefinitum, and the synthesis progresses as long as there is a manifold of intuition, blah blah blah, etc. So what's actually so as long as there is a degree of perception. So what basically prescribes what is prescribed basically by the principles of the pure understanding. So that's a thing that stimulates me in with respect to what you said. Because it seems to me, I agree with you with the fact that the Châtelet and Kant are not that far at all in these considerations. However, I think that Kant, I mean, we cannot deny it in a sense. He had a more sophisticated way of handling of producing arguments for or against, let's say, the metaphysical or the metaphysical rendering, so to speak, of the mathematical notion of infinity in philosophy, because that's the intriguing point. So when introducing the solution to the antinomies, he clearly says we have to use the philosophical notion of infinity, which coincides with what? With a synthesis in indefinitum. And the point is that whereas it's less problematic to say that the world with respect to space and time is indefinite, in terms of extension, let's say, so extensively, intensively, he says, well, let's say that we're not just happy by saying that matter is divisible in an indefinite, manner, or at infinitum. It's ad infinitum. It's like as long as we, but not as singular, particular individuals, but as long as we, it's sort of, we like species who's organized in society and does science, okay, as long as we continue exploring empirically the parts of the whole, then we can say that matter is divisible infinitely, but in a very, very specific, by assuming this term infinity in a very specific way. Also, what's interesting is that he never says that the parts of matter are infinite in number, but he says, of course, that is the synthesis that can produce an infinite number, let's say, of partition, as long as the synthesis continues. So that's my point. But of course, it's we can debate about it. It's not.
Yeah, I don't think we disagree, because I think anyone who's not Kant in the antinomies would regard what he says about the infinite divisibility of material wholes into parts as a potentialist conception of infinity, where there will never be an infinity of parts. there might be an infinity of activities if we somehow transcended our finitude and were able to keep dividing and accomplish a super task. But I don't think he ever says that, or could say that there actually are an infinity of parts. But you're right that there's a structural difference he's trying to establish that's very difficult to understand between the case of the whole world expanding outwards in space and time, where maybe that is truly indeterminate, whereas, yeah, he says that in the case of the parts and wholes, in some sense, the parts are always already there, but they're not really determinate parts yet, he must be saying. So I think it's still a kind of potentialism, and so in the end, they're more similar than they disagree. But I did want to get to your other questions too. So maybe I can, since we have the continuous function definition up right now, I guess, well, I probably can't answer it fully, but maybe I was being a little cavalier in the bottom bullet point by saying that she exploits the entirety of this definition to argue for the divisibility of space, time, and matter. She really does not need the everywhere differentiable part. Like, at least the way I reconstructed the argument very briefly and when I was talking, she really is just arguing from this idea of a continuous process in the sense that we would understand it, where the process, like the motion, is proceeding through space and time, and therefore you need an indefinitely divisible space and time to accommodate that process. And you don't, to run that argument, you don't really seem to need this smooth graph condition of the everywhere differentiability. So I think it avoids your objection, but maybe it also means that her strongest definition of continuity is not actually playing the argumentative role she thinks it's playing. So maybe I should rephrase this as she takes herself to be exploiting this definition to make this argument. So she conceives it as this definition is more fundamental, but maybe you could use a weaker definition of continuity instead. So then finally, the physical monads question, that's a big question. So, I mean, well, first we have to acknowledge, the first point is that this is 1740, 1742. So Kant has not even started writing his first essay on living forces, which responds to Châtelet. Probably the monadology is not yet even a glimmer in his eye or whatever. So this is prior to that. But we can look at Wolff. So you might, in a more extended sense, regard Wolff as some kind of physical monadologist, because Wolff infamously distinguishes two kinds of simple substances: the ones that are more soul or mind-like and more like Levitzian monads, and others that are somehow more physical seeming. They seem to have forces in a pretty straightforward physical sense. Problem is, after that, things get very hard to understand with Wolff, and especially the puzzle of, the labyrinth of the continuum is not a labyrinth that Wolff really escapes in a satisfactory way, as far as I can tell. I mean, maybe other people are more optimistic, but it's really hard to understand what he thinks there. So he does seem to try to say that, in some sense, the simple substances in Wolff literally compose matter, but it's not clear how. It's very weird, and he doesn't have the Kantian trick of having each physical monad occupy zero space and be unextended, but have it in some other way fill space via exercising force. Wolff actually can't do that. This is like a classic Marius standpoint, because Wolff denies any action at distance. Like, for Wolff, every force has to be act by contact. So he couldn't have taken the Kantian option. So then the question is, how do things stand with du Châtelet? So I would say that she also, at least at the level of phenomena, is a Wolffian about force, not a Newtonian or a Kantian. So she is also very skeptical about at least fundamental forces at a distance. We saw that passage about the physical qualities. She thinks that you can accept gravity as a physical quality, but that's maybe not fundamental. We're always going to be looking for some possible contact action explanation of that. So she conceives of matter, like Wolff, as exerting two forces of attraction and repulsion, but always through contact. So she couldn't do physical monads either. But then there's a question which I don't want to resolve in this talk, which is, how does she fully resolve the labyrinth of the continuum question? Like, how does she compose extended matter out of simples? So Marius Stan thinks it's literally composition, like mereology, just like in Wolff? I don't think so. I think she's more like many readings of Leibniz and basically all readings of Kant, where it's more like it's not mereology, whatever it is. It's some kind of grounding or different levels or something, where du Châtelet's simples are really not in space and time at all. They're not just unextended components of matter. They're on some other level, and they ground matter, but they aren't literally composing it. So that's what I would prefer. I think it makes it a little easier for her, or maybe it just cuts the Gordian knot by like just refusing to address composition and switching to a different relation. But so I think she's not Wolffian with respect to the composition question, but she is Wolffian about forces, and that would be sufficient to make her not able to do Kantian physical monads, because you need action and resistance for that.
Yeah, no, indeed, I was thinking about Baumgarten.
Oh, Baumgarten. Okay, so that I don't know so well. So what is that? Is that different from Wolff in some?
Of course, because I mean, I think that
I don't think she read Baumgarten, by the way, but
no, indeed, this is something that you could check.
Okay.
Because it's 1739. He published. Yeah, so that could be interesting.
In Latin, right?
It could be interesting to check whether she, in a way, in an indirect way, maybe, we don't know, but still one can check this, because of course, as you said, as you correctly said, it's clear that she was not aware of Kant's position, because Kant was at that time was not certainly.
No, yeah, I mean, I've looked, so we don't.
It's not what, but my idea is, okay, there must be, there could have been an intermediate Wolffian or an intermediate Leibnizian, so Baumgarten could be a good candidate for it, also because he extensively talks about physical monads that could have, I'm not saying directly influenced her for many things, but maybe on these questions, there could be some, effect, let's say.
Maybe, yeah, I just don't know. I mean, there are like a few sources for knowing what books she had. She has letters where she tells her publisher her books and orders more. And then there are inventories when she died of her books and Voltaire's books that were there too.
Yeah.
And none of those have Baumgarten. But that doesn't rule it out. It's just I don't know of any positive evidence, and I don't think she
have you checked, for example, I mean, in the case of Kant, it works pretty well. Maybe also in the case of the Châtelet could work. So sometimes there were published some abstracts or resumes, so some summaries of works published, I don't know, in German or abroad, in this case, so in France, they could have published, in journals, some abstracts, from Baumgarten's work. So that,
but was he? I mean, my sense is that Baumgarten was not like very important. I mean, he was for Kant, because Kant lectured on his.
No, of course,
but he wasn't like a. So, for example, like the main players in the monad controversy were people like Euler, who were famous, whereas Baumgarten outside of Germany would have just been regarded as like a obscure bumpkin textbook writer, right? Like, that's my sense. So I don't know why. Maybe she would read this, but I just feel like she wouldn't have cared if she knew, but maybe, I don't know. I could look into this. It's an interesting, but no, I would like to know though, like, is there a specific Baumgartnerian twist on the simples or physical monads that's not involved? Like, what should I be looking for?
Well, I think that you should look at so the way in which Baumgarten portrayed extension, so the relationship between extension in space and living force.
Okay.
Yeah. So because it's and also this idea, this sort of epistemic reading, okay, that she gives about space and time. I think it's worth being compared. Yeah, well, anyway, I maybe we can continue this chat. I don't know whether we are just the three of us, so okay. Well,
okay.
actually, thanks a lot, Aaron, for your talk, and
Thanks. The comments, both of your comments and the other comments to those who are absent, they were really helpful. Super great. Yeah.
Yeah, let's hope to see each other in the future, in the near future. And thanks a lot again.
Yeah. Thanks again for inviting me.